Hello everybody, my name is Ben Specksnyder. I'm a research assistant at the Swedish University of Agricultural Science, or SLU, and I will talk to you a little bit about biochar and the application towards the removal of organic micropollutants, or OMPs in short. So, today I will talk a little bit about what is biochar, give a little introduction on why we want to use biochar, a little on our research, what we did with biochar, and then I will give you a little bit of an outlook and give you some other examples on usage of biochar. So to start, what is biochar? So biochar is a simple concept. It is taking a biomass and then performing pyrolysis on it. Pyrolysis is basically heating it up without the presence of oxygen. The most famous one we all know used for a grill is like charcoal. This charcoal is basically made using a form of pyrolysis. However, to make biochar, the biomass can be of different types of waste products usually. So it can be of sewage sludge, it can be of forest waste, wood type, but also coconut shells, animal manure. Think of any type of waste products that they can be go under pyrolysis, and you can make a char out of it. So, but these biochars, they are very different, and there's two main factors that play a role. Of course, first you think biomass. Biomass is a big thing that introduces a lot of variability. Think of forest waste, which is a very plant-based. Plant cells have a way different structure than things like sewage sludge or animal manure. Like they contain different types of cells, different types of main components, so the biochar will look different. Secondly, we have also the pyrolysis is highly different. You can go from temperatures from 200 degrees up to like 900 degrees, and depending on this temperature and also how long it is in the oven, you get very different types of biochars. So now let's zoom in a little bit on the biochar. So a biochar, when we zoom in, we see different types of pores, macro and mesopores, and these pores really depend on how you make the biochar and what type of biochar it is. So one key factor is this pyrolysis temperature, and we see that when we increase the temperature by a lot, we see that this specific surface area, which is a measurement for the how many pores basically the biochar has, is increasing. Other factors we see with increasing temperature is that the carbon ratio is going up. So this in fact leads to a higher carbon to oxygen ratio and a carbon to hydrogen ratio. So what does it mean? So these ratios tell us a bit about what is on the surface of the biochar. So if we have a very high carbon content, it's mainly aromatic surface we have, but if we have a higher oxygen and hydrogen content, it's way more polar. So the surface, what the surface looks like is very important, especially if we want to do some type of removal with the biochar. So when we look at this biochar, like how do we know which type of biochar to use? What is a good biochar and what is not a good biochar? Because we want like the top biochar that absorbs a lot of pharmaceuticals instead of the bottom one that can't absorb a lot of pharmaceutical waste. So, so if we look a little bit in what type of processes are going on, here you have this amazing review paper. If you really want to learn more about this process, I recommend reading this one. Here you have different types of interactions. So you have electrostatic interactions, you have polar interactions, you have hydrophobic sites and interactions, and these type of interactions mainly become a large role if you have these. So these electrostatic and polar interactions mainly are important if you have higher oxygen and hydrogen content. If you move more to a very high temperature biochar, where there's mainly a high carbon ratio, we see that this partitioning in the non-carbonized phase, so basically the organic micropollutants travel inside of the biochar, that one becomes way more important. And of course you have also this hydrophobic side and this non-polar interaction and like things like pi bonding, and those also become usually a bit more important when the carbon ratio increases. So why do we care? Why would we want to use? So a little bit of background. People use a bunch of pharmaceuticals, and these pharmaceuticals, they end up in our body, and once we go to the toilet we excrete a lot of these pharmaceuticals, and a lot of people unfortunately throw a lot of their pills in the toilet as well. So a lot of pharmaceuticals come into the wastewater and they end up at a treatment plant. So treatment is not really designed to remove these pharmaceuticals, so usually after the water has gone through the treatment plant, it's just released into the local rivers, or in worst case, it's sometimes even used as irrigation for agricultural use. And of course, this is what we want to avoid. We want to avoid as much contamination as possible, and this is what the European Union wants to avoid as well. So this year, actually, the European set up a clean water directive, and the goal was to remove over 80% of the organic micropollutants from the wastewater influent. So it means that 80% of the incoming pharmaceutical contaminants or organic micropollutant contaminants need to be removed. On this list are, why I keep talking about pharmaceuticals, are mainly pharmaceuticals. So the goal of this Clean Water Directive is, of course, to protect the environment and protect human health and aquatic health. But there's also other ambitions in this water directive, address climate change and advance circularity. So we want to not only clean it, but we want to clean it in a green and proper manner. So this is where our biochar comes in, because there is a common technique known as granular activated carbon, or GAC, that has been proven amazingly at removing organic micropollutants. So, however, this one has quite the negative effect on global warming. It has a negative CO2 impact. However, if you compare it to biochar, since biochar is in generally made from waste products like sewage sludge, we see that we can gain a net energy gain, and we can even have a positive effect to global warming, because it's much better if these waste products don't rot on a waste pile or a landfill, or put on or thrown on onto agricultural land. So in this way we can have a more positive effect by turning waste into something stable and valuable, like a char. On the other hand, the activated carbon is quite expensive. It's an expensive process to make, and compared to biochar, it can be about 10 times more expensive. So from an economical standpoint, it's also very interesting to look at biochar. But there are some downsides, like biochar, as I said before, it's so complicated depending on which type of feedstock, which type of preparation you made. So there's some high variability, and a lot of study needs to be done to show what the long-term capabilities are. And if you compare this to GAC, there are a bunch of studies already that show that GAC is a good long-term absorbent. So in our study we try to bridge this gap a little bit. So we made some columns, and we filled this with biochar. So we filled this with 5 different types of biochar, and we had some gravel columns as a control. And with these columns we put wastewater, effluent, we spike this with a set of pharmaceuticals to make sure that we can trace these pharmaceuticals well, and then we let these wastewater flow through our duplicated biochar columns for a long time. I think we run the experiment for almost a year, and here on the left you can see a column that's filled with biochar. So what does this tell us? What does it say? So we sampled about every day or every other day we took a sample. And in these samples we measured pharmaceutical concentration of a bunch of pharmaceuticals, and this is kind of what you expect to see. So this is from a nice paper that if you're interested can give you some more information about the breakthrough process, because that is when the breakthrough process is when basically we absorb a certain amount and then at some point the absorption stops and then we have a breakthrough, so some leakage or some concentration of the analytes or the pharmaceuticals you want to absorb is pushing through. So here we see this in this graph as well. We see, let me break down this graph a little bit. So on the left, on the y-axis, you have the concentration that is coming out of the column over the control concentration. In our case, we use the gravel concentration to make sure it's normalized over other circumstances like light, temperature. And on the x-axis you have a form of time. So here in this example you see that the column is slowly loading with contaminants, and at some point these contaminants start to leach through. The rest of the column can still absorb to some extent, but at some point the column is completely saturated and then you get a full breakthrough, or the control column, the concentration in the control column and the concentration of your normal column should reduce to 1, as they don't have any effect on the pharmaceutical concentration anymore. However, in practice, when you work with real wastewater, things get a little bit more complicated. So here we have a similar type graph on real data, and here is basically the breakthrough curves of all the pharmaceuticals that we measured, and then here we have the median, the first and the third quantile, to show sort of the variation between all the pharmaceuticals. So from this graph you can see that the individual pharmaceuticals show a lot of variation already. So absorption is very pharmaceutical dependent. To explain this graph a little bit more, on the x-axis we see now bed volume, and bed volume is sort of a measurement for the time. It basically says the amount of column volumes that has gone through the column. So this is basically a way to sort of normalize this type of data. So in case we had very big columns of, let's say, 1,000 liters, then we could say, after 200 bed volumes, which would be 200 times 1,000 liters, so 200,000 liters, we have about 50% breakthrough. Of course, in practice, it's not always as easy as that, but this way people can compare their work between one another, as different column sizes and different flow rates are applied. But still, bed volume you can see as a sort of measurement in time. So we measured 5 different biochars. So here I picked 3 of them, and you see that even though all the biochars were fed the same wastewater, we see that the breakthrough behavior is very different. So for this left top biochar, the one which I showed earlier, we see quite an early breakthrough already from the beginning. We see some pharmaceuticals leach through, and reaching saturation around 300 bed volumes. For this pine and spruce biochar, we see that it does absorb for quite a while. However, slowly we see that this breakthrough is happening, and then we're slowly moving towards the saturation point. On the other hand, the sewage sludge biochar, we see that the pharmaceuticals are basically absorbed for the whole 11 months, which is also interesting. So absorption and absorption capacity is very dependent on what type of biochar you have as well. So I also talked a little bit about the difference in the pharmaceuticals, because here you see pharmaceutical deviation as well. So let's pick out two pharmaceuticals. So here we have two pharmaceuticals that are quite commonly found in wastewater. One is carbamazepine on the right and clarithromycin on the left. And to make it easier to visualize, we fitted a common breakthrough model that Hugh Nelson threw it. And we can see, if we look a little bit at these pharmaceuticals in depth, we see that the one on the right, carbamazepine, is quite a small pharmaceutical. It has a molecular weight of around 250, while on the left, clarithromycin is a very big antibiotic of around above 700 Dalton. So in comparison, we see there's a massive size difference. And this size difference it's interesting, as we see this clarithromycin has a very much slower breakthrough compared to carbamazepine, even though they're for the same biochar. So we see that there are differences in the properties of the pharmaceuticals as well that affect how fast or how slow the breakthrough is on the biochar. So when we look a little bit into the biochar, we know that biochar is mainly negatively charged on the surface. So, and this correlates with our results as well, because when we look at the different pharmaceuticals we measured, we see that absorption improves for positively charged pharmaceuticals, and negatively charged pharmaceuticals, they don't really like to absorb so well onto the surface. On the other hand, we also see, as previously shown, that the absorption does seem to increase with size. As the pharmaceuticals become bigger, when they transfer into the pores, it's harder to move them out. However, there's one important thing, is that pore size matters a lot, because the pore size can become too small for these big type of molecules, and then these bigger molecules can't really participate into these pores, and then they basically get pushed through. However, in our case, this was apparently not really the case, and this might be more prevalent for bigger molecules like some antibodies or proteins. So if you're very interested, I recommend that you read more in our study, which hopefully will be published very soon. So now to look a little bit on other usage of biochar. So as I've shown you, wastewater/water remediation, you cannot pollution in water is not only limited to wastewater. There's a lot of other sites which biochar can be very prominent in. For example, for the removal of metals. Metals are generally positively charged, so this negatively charged biochar could be very helpful for the removal of metals, especially in like contamination from like mining industry or other places. Of course, there's been study on the removal of organic micropollutants in different types of other matrices, and of course the removal of PFAS has been a hot topic. However, PFAS is a bit more tricky, since PFAS usually has a negative head group, so absorption on biochar is not always the most efficient way to remove PFAS. Then there are other usage, common usage I think one of the most common usage is to have it as a soil improver. Biochar also has this water retention capability, so it can, when you put it in soil, it can hold water and make the ground more fertile. There's also been studies going on in putting biochar in contaminated soil in the hope that there is some remediation going on. There's looks on using biochar in building material. This is part of a way to have some carbon storage as well. Since we turn waste into a solid carbon, we can basically reduce the CO2 emitted, and this is a very common use to get carbon credits. And then if we use this biochar in building material, for example, we can fix this biochar and fix this CO2 for a long time. So these are kind of the application of biochar and why biochar is such a hot topic, and you might have heard a lot about it. So now let me give you a little bit of an outlook, a little bit of a dream view, so to say. So let's review back. We want this European Clean Water Directive, right? We want to remove 80% of the organic micropollutants. However, currently, when we look at the European Union, it does not allow the large-scale usage of sewage sludge biochar. And why am I so interested in sewage sludge biochar? Well, in our study, for example, we saw this great performance, and besides that, sewage sludge is a very prominent waste product. Every person, every city has a lot of sewage sludge, and most of the time the sewage sludge is just used for agricultural land or just put even on landfills. So there's a lot of excess sludge that could be, instead of a waste product, it could be used to create a valuable product like biochar. And an even ideal solution could be to use it directly in wastewater treatment. So you have your sewage sludge, we perform some digestion and drying on site. This digestion gives you biogas or methane, and this methane can use directly into the biochar production. And this way we can have a production on site that is basically doesn't cost any energy except to start the pyrolysis, and then it should be a recycling project, recycling its own energy, and then we produce this biochar that we can use immediately in water treatment. So this way the wastewater treatment plant can deal with its own sewage sludge, and it saves a lot of disposal and a lot of problems related to that, and they have a way to clean up the wastewater. So I've shown you a little bit about the potential of biochar for the removal of organic micropollutants. There are still some limitations as we need large-scale pilot tests to really show how this could work over the long term, how we could improve and how we could implement it in our treatment facilities. Furthermore, this requires some political approval. There are some countries that are moving especially towards the use of biochar, but also the use of sludge biochar are more open to this. Think of countries like the Czech Republic, where they approved the usage of such biochar. But to make it a more European-wide thing and to really boost the usage, I think we need more knowledge and more information, and hopefully in the future we can use biochar a lot. So thank you all for listening. I hope you learned something, and if you're interested, feel free to contact me on LinkedIn or whatever. Have a nice day.